Okay. Next, we're going to go to Stephen Hamilton, KJ5HY, and Charles Suslowicz, KD2RQS from Westpoint, with visualizing the electromagnetic spectrum in the time domain.
Okay, hello.
Right.
Can you hear me?
Mm-hmm.
Okay. Yeah, so can you play the video? Do you have
I
it?
most certainly can.
Okay, awesome. Greetings, everyone. I'm Stephen Hamilton, KJ5HY, and Chuck Suslowicz, KD2RQS, also helped with this project of graphing in-phase and quadrature, or IQ, data from an SDR into 3D space. We began by using the Visualization Toolkit, VTK, and Python to read the IQ data and convert it to points in 3D space by putting the I and the Q on the X and Y axis, and then creating a time axis in the Z direction. So first I'm going to show you, this is the script that we have, and thanks to Chuck, he helped me create the arguments here so that it's a little more user-friendly, because before it would just crash if you didn't put a file in. So now we know here's all the arguments you can do. We had to add a z-scale because we found that we were playing with that a lot to try to get this to look right, and also the sample rate, because sometimes you'll sample at different rates and you want to make sure you get that correct as well. We also added this idea of adding I and Q on the X and Y planes, which I'll show that in a minute. Okay, so I'm going to show you one of the first ones that we did was this FM low 2X. So basically, I took a handheld transceiver in the RTL SDR and just listened to that frequency, recorded the IQ data, and transmitted 2 times. So after I did that, we'd run it through the program. It does a few sanity checks to make sure that it's actually getting the I and Q, and then it creates a VTK file that I can use in pair view. So now I'm going to switch over to pair view. We'll be done with the Python now. There's pair view. I've already got some of these preloaded just for the sake of time, but I'm going to load this FM low 2X. You can see the one that I just converted right now. So we looked at this, and this was really, really exciting when we first saw it, because now we can see visually that there were 2 distinct transmissions. We weren't too happy about how messy it was. There's also a weird break in it as well, which I'm really not sure what caused that. But the good thing is we did prove that we were actually getting the IQ data and plotting it, and it seems to start to make sense. So after that, I did another transmission, and this one I was real close to the RTL SDR, and you could see some really weird artifacts that happen here. It turns it into 2 boxes. So the problem with this is I think it was clipping is what probably makes the most sense. So I basically were maxing out the I and Q values, and so just totally clipped the transmission. So this was good because we saw a difference as you get a stronger signal. That's why the other one was called low, because it was a lower signal. I actually had to take the antenna off to keep it from over modulating like this. Okay, so the next thing is we had to use a generated IQ data from GNU radio. So this is QAM 16, and this is perfect. Like this shows that we're doing this correctly. I just generated inside of GNU Radio, recorded it straight to a file sync, and then ran it through our script. So after that, I said, well, maybe we need to check out a different SDR. So we moved to a Midwest Microwave Solutions SDR, and that one we did some FM voice. This looks a lot cleaner. You can really see the signal here, which was pretty exciting. You could see, it looks like FM, kind of what FM you would expect to look like. The frequency looks like it's changing right in here. So that was good. It's good to see. So that got us excited. So we decided to say, well, what other types of modulations would look neat? So we went up and did RTTY, which I had to use the Noelec, and it was a transverter that we used to bring up the frequency so the SDR could receive it. And this worked out really nicely. This was real pleasing to see because now we can really see that modulation. It was very clean. This was done with a FL Digi and the Electromagnetic KX3, and then just recorded with that Midwest Microwave Solution. So this was real exciting to see when we did that. Next one we did was QPSK. You can really see the amplitudes changing here real nice on this one. And so this one I'm going to show, since this one was probably one of the neatest ones that we got so far, I'm going to show you adding those other components. So if we go to this next one, this is probably the nicest looking one I have. So I've added that I and Q on the side so you can see how that's graphed. I've also converted them to spheres. We found that that looks kind of, it gives you a little more feel of what's going on. That's like textbook quality. So this was real exciting to see that we got this. So this is a real generated signal that we recorded. Obviously we were close to the SDR, but it didn't overmodulate and it just came out as a beautiful signal. So that's our project, and I guess we'll move on to the questions section.
Are the, could I ask a question?
Please go ahead.
Yeah, I have worked with the VTK stuff in the past, not with Python VTK, but I wondered if those algorithms are fast enough on current computers to do anything useful in real time.
I think I knew somebody was going to ask that. Great start for the questions. I've been thinking about this, so it is pretty slow, as you saw. If you have a GPU, that rendering I was showing you was rendered with the GPU on my son's gaming computer, and it worked out a little bit better. There's a catalyst which allows you to connect to simulations in ParaView. I'm trying to figure out if that's possible. I think if we did that, we would probably have to reduce the sample rate. There's just so much data that's created that I don't know. I think the way to do it is to figure out how to do it in the GPU, and I'm not really sure. I'm not really sure it could handle the bandwidth coming in as a problem. It's always an I/O problem when you deal with these large data sets. So, but it's not to say it can't be done. I mean, those transmissions were really short. As Chuck and I were messing with it, I was trying to keep them under 100 megabytes, just because we were transferring them around, and they're just within usually 2 to 3 second transmissions. So I think that would be interesting. That's something that I'm interested in doing, but I just got to figure out how if we could figure out what's most important, or maybe we decimate somehow and then just link the points. There's maybe some way of doing that.
It's a simple graph. I'm surprised that possibly even just a digital sampling scope, you might get to do it in some way.
Well, yeah, it seems simple, but there's really like quite a few points on it. I can actually give you an idea here. Let me see. That last one had 23 million points. So yeah, that's a good question. I'll have to I'll work with Chuck and see if we can figure that out. But it's pretty dense. And the last one, like I said, if I didn't have a GPU, I couldn't even rotate it very well.
N0AX with a question. When you put the constellation up there of the 16 QAM signal right at the beginning, I immediately flashed over to coding, and there's some really interesting geometric work on braid theory, BRAID, and whether braids are sort of a three-dimensional thing, and I'm wondering if there are properties of braids that are linked to properties of optimum coatings, like Viterbi coatings and various other things like that. Seems like this presentation would be really handy for visualizing the link between those two sort of disparate areas.
Oh, I'm going to look that up. That's really interesting. I have not heard of that before, but I'm going to look that up and see if there's something there. That's kind of the next step, is we're really looking at what kind of artifacts. I mean, the initial goal of this was to look at what kind of artifacts exist in IQ that just get lost in the FFT. And I was, immediately we looked at phase as being something that's kind of obvious, but yeah, that would be interesting to look at. I'll Google that.
This is Phil. Steve, that's really impressive visualization. You know, I was giving a presentation yesterday at this conference and talking about pseudorandom codes, right? Where, you know, the phase is essentially random from point to point, and in fact, the more random it is, the sort of better signal it is for doing ranging of something. I could see you be able to use this in that, you know, now along the time axis, you could sort of see that as the points are random, for the longer the time you use, the more a random collection of points you have. It's harder to show that in a 2D sense because you've just got I versus Q, and you have to just keep showing it at different times and let people see that the points are building up. So I would encourage you to try just random binary codes in that same format, and it's a nice, useful comparison to more deterministic codes like the ones you've already shown, like quadrature amplitude or FSK, other flavors of FSK.
Okay, yeah, I'll look into that. I have not done that yet, but that could be interesting. Yeah, you're right. That was the thing that I've seen before. Is the IQ is usually flashed in time, and actually in VTK VTK you have these you have time steps, and we didn't do time steps because we put it in the z-axis. So I was almost interested in watching it in time steps to see that 2D view of the same exact signal, so you could see. You could actually judge that difference. So we might take a look at that as well.
Great.
David, AD8Y here. Did I interpret it correctly that the RTTY signal generated by FLDigi had quite a bit of it?
I didn't quite catch the last part of your question.
It looked like the frequency transitions that FLDigi generated for the radio.
David, we lost the last part of your question. Your microphone stops working before you're done.
Okay, I'll try again. Did FLDigi's radio teletype generation put some amplitude modulation onto the frequency modulation as well? Am I interpreting that correctly?
So that's something that Chuck and I were working on. That's why I didn't have a good example yet of FM and AM, because we also noticed some of these kinds of these things, and I'm not sure. It does look that way, and that's kind of bothered me. We were looking at just an AM signal, and we kept seeing some phase shifting going on that we didn't think was supposed to happen as well. So I got a little more work to do to really, because I used if you go to RTL SDR's website, there's a IQ applet that I think somebody made. There's a link off of it, and you can actually watch what it should look like, and that's what we used kind of as a guide. But I can't make I haven't been able to make the FM and the AM even look quite like that, and it may be a scale problem of us looking so far out, and maybe if you look real closely, maybe that's the way it's supposed to look, or I don't know, maybe I'm interpreting something wrong. But yeah, oh yeah, I see in the chat Chuck's talking about this. So Chuck was working on this with me, but I would have shown you FM AM, and I did do CW this morning. I finally got the system up and running at my house, and I was seeing like a square wave like we would expect, so that was good news. But my AM still looks kind of strange, and you're right, the RTTY didn't. I don't know. It does look like there's amplitude modulation happening.
Steve, just before we move on, people have already asked, where can I get the code?
Yeah. It does exist on GitHub. It's on a private repo, but I can make it public. I'll put it up. I'll talk with Chuck about it. We didn't want it out there until luckily Chuck helped me clean it up. It was incredibly unuser friendly and just not intuitive. But it's now to a level where we can play with it. So I'll before the end of the conference, I'll get with them and we'll see if we can just unlock that or move it. I'm not sure how hard that'll be.
Any final questions? We've got about 4 minutes. All right, in that case, we'll move